So we had learnt about materials which have just one plane of symmetry, monoclinic materials. Uh, then we have learnt about orthotropic materials which have three planes of symmetry. And then transversely isotropic materials which has a single plane of symmetry but is completely symmetric, completely isotropic in the other two planes. So so taking this idea forward, we have seen that as you add more and more symmetries to your material, the number of elastic constants that are needed to specify the material properties keeps on decreasing. The most general case is 21, then it comes down to something like 13 to 9 to 5 for a transversely isotropic material. Now, what happens if there are no preferred planes, which means that no matter what kind of a transformation I do to the stiffness matrix, so this is the transformation from an old coordinate system to a new coordinate system. No matter what this q is, I always get the same number. I always get the same number. So this and this are always equal no matter what q is. That is a material which does not have any preferred plane, any plane of symmetry. All planes are planes of symmetry. So this is called a completely isotropic material that has no preferred directions inside it. So the most general form of a fourth order tensor, which is completely isotropic and behaves and has this property that any rotation tensor would always give you back the same components, same values of the components, and the most general form is given here. So the most general form is given in terms of the Kronecker deltas. Alpha, beta, and gamma are arbitrary constants. You can have any values of alpha, beta, and gamma, and you will get a completely general fourth order tensor, which will not have any preferred directions, any rotation or deflection will lead to the same sets of values of the elastic constants. However, for an elastic material, um, I need to have symmetries. So for example, Cijkl will be equal to Cjikl. And if I use that, Cijkl equal to Cjikl, so I just switch I and j here, then I will see that these two terms, so see this will become, if I switch, this will become delta ki, delta jk, and this will become delta il, and this will become delta ik, and this will become delta jk, and this will become, I'm messing it up. This will become delta JL, and this will become delta IK. This will remain delta IJ because it's a symmetric tensor. So this will remain delta IJ. So this is what you will get if you switch I and J, and obviously Cijkl and Jikl are equal, which leads to the conclusion that beta and gamma are the same. So you can reach that conclusion by switching KL also. KL equal to LK, you can use that and you will come to the same conclusion that beta and gamma have to be the same if we need to have the minor symmetries of Cijkl, which means that there are only two undetermined constants now in Cijkl. For a completely isotropic material, the number of independent constants required to specify the stiffness completely comes down to just 2. So we started with 81 major minor symmetries, brought it down to 36, then orthotropy, monoclinic, transversely isotropic, etc., brought it down to 5, and complete isotropy brings it down to 2, and 2 is what we are going to stick to. So we are going to deal with linearly elastic isotropic materials only, mostly in this course. So so we are going to rename these constants. So this alpha, we are going to call it lambda, and beta and gamma, we are going to call it mu. And we will write the isotropic elastic tensor in this form. in this particular form. This is the most general form which satisfies the minor symmetries of CIJKL. Okay. The quantities lambda and mu are called namis constants. These are called namis constants, and these are important material parameters that you will have to determine experimentally in order to characterize a linearly elastic isotropic material completely. Okay. So now how do I write the stress strain relation? It's easy. So I write sigma ij equal toCijkl epsilon kl. This still holds. And then now for an isotropic material, this is what I will have times epsilon kl. And this will lead to, just let's do the multiplications. So lambda times delta ij, delta kl epsilon kl will give you epsilon, let's say mm. So I'll have delta ij epsilon mm from the first multiplication. Then I have mu times uh, delta jk delta il. So k will be knocked off for j, so you will have epsilon j, and l will be knocked off for I, so epsilon ji, plus this l will be knocked off by j and k will be knocked off by I, so you will have ij, but then these are symmetric, so you will be left with lambda delta epsilon mm delta ij plus 2 mu epsilon ij. So that is what you have here. This is your isotropic stress strain relation for a linearly elastic material. So very special case, but then this is very popular, especially when dealing with metals, because most ductile metals that are used for structural purposes turn out to be isotropic or very nearly isotropic, and um, bulk metal, not sheet metal. Sheet metal is very often not isotropic, but bulk metals are mostly isotropic. Many polymers are isotropic. Um, Many other materials are isotropic, though there are lots of non-isotropic materials, but most structural metals and polymers are isotropic at the level of small strains. At the level of small strains, they are isotropic, and this turns out to be therefore a useful relation to analyze a whole lot of materials under a whole lot of loading conditions. Okay, so this is the stress strain relation. This is so this is called the stiffness. This is called the stiffness. This is the stress strain relation. Also called the constitutive equation. And these are your two constitutive parameters that needs to be determined from experiments, will vary from material to material. Just like the stress strain relation, we can calculate the strain stress relation also, and that will be called a compliance. So we have now determined sigma ij equal toCijkl epsilon kl. We call this the stiffness. We can do epsilon ij equal to Sijkl sigma kl. So this is also possible. This will be inverse of this, and this is called the compliance. Sijkl will be called the compliance tensor. So generally, it's not very easy to if you have a general situation where you don't have all the symmetries, it's not very easy to invert this. But for an isotropic material, it turns out that it's possible to invertCijkl to get Sijkl, and that's what we are going to do now. So first let us look at the stress strain relation, which is sigma j equal to lambda epsilon kk delta ij plus 2 mu epsilon ij. This is what we have determined. So let us look at it for the case where both I and j are equal to each other. So they are both same. So I have, let's say, sorry, need some space. So I have, say, sigma mm equal to so here this is, we know, 3. So this is 3 lambda, and epsilon kk and epsilon mm are actually the same. They are the sums of epsilon 1 1 2 2 3 3. So I have 3 lambda plus 2 mu epsilon kk. So I have sigma kk and epsilon kk related by 3 lambda plus 2 mu. Okay, so let me rub off the rest. Okay, so then this is a scalar quantity. So so is this and this. So sigma kk is the sum of the diagonal components of the stress tensor. Epsilon kk are sum of the diagonal components of the strain tensor. So epsilon kk is sigma kk divided by 3 lambda plus 2 mu is what we get. Now we go back to our stress strain relation. Epsilon kk, we will replace it with sigma kk divided by 3 lambda plus 2 mu, and then we will express epsilon ij in terms of sigma ij. So this is what we are going to do. We are going to use this last expression to plug it into epsilon ij, and this is what epsilon ij will turn out to be. So this is what we can get by just transposing terms and replacing. This is quite easy to get. Try it out. Now once we have got this, we will try to isolate. Remember, we are looking for a relation which is of this form. Epsilon ij is Sijkl sigma kl. So we are looking for the Sijkl. We have a relation between sigma epsilon ij and sigma ij, but it's not in this form. So we will have to bring it into this form. To do that, I will have to take epsilon kl out from here. That is not difficult. So I will have 1 by 2 mu. Then sigma ij, in place of sigma ij, I will write, firstly I will use the symmetry. So I will write I have used the symmetry of sigma ij, and then minus I have lambda by 3 lambda plus 2 mu into sigma kl is what I want out. So I will write this as sigma mm delta ij to start with. Okay, so then I have 1 by 2 mu I want to turn this into sigma kl. So what I can do is I can write it as ikjl sigma kl. Then I can write this as delta j k delta il times sigma kl. So I can write it as this minus lambda by 3 lambda plus 2 mu, and I can write this as delta mk delta ml delta ij sigma kl. This is what I can write, so that I can now take sigma kl out. If I take sigma kl out, the rest of my stuff is Sijkl. So I take sigma kl out from here, and I also see that this becomes delta kl. So I have minus lambda times 2 mu into 3 lambda plus 2 mu, that is what I have here, times delta ij delta kl, that is what delta kl delta ij, and then I'm left with this times 1 by 2 mu, so 1 by 4 mu times this quantity. So this quantity is like that case that we did long time back. We did a derivative like this, and for a symmetric tensor A, and then we use this trick there. We use this trick there, and we are using it again here to get the Sijkl. So that follows because sigma ij is symmetric, and this is your compliance. This is your compliance. And compliance is the strain stress relation opposed to stiffness, which gives you the stress strain relation. Now you know that there are two constants that are required in order to define the properties of a linear elastic isotropic material completely. And these two constants that we have taken into account are called namis constants, and we have called them lambda and mu. These are namis constants. However, namis constants are not always easy to measure in an experimental setup. We have standard experimental setups to measure the properties of a linear isotropic elastic material. And lambda and mu are not the best possible choices. There are other choices that we can use, and we have to have two numbers, and there are many choices that we use, and very often we need to convert between the different choices. So this table here is a conversion of different constants in terms of different others. For example, we sometimes call so this quantity here actually relates epsilon kk, which is del u1 del x1 plus del u2 del x2 plus del u3 del x3. This is epsilon kk, and you can show, or you probably already know, that this is delta v by v, known as also the volumetric strain. So the trace of the strain tensor is the volumetric strain. This, on the other hand, is sigma 11 plus sigma 22 plus sigma 33, which is the trace of the stress, and this is sometimes called 3 times the pressure. This is sometimes called the pressure. So this quantity divided by 3 gives you a pressure by volumetric pressure against the volumetric strain. So this quantity, which relates pressure to the volumetric strain, is sometimes called the bulk modulus. And the bulk modulus can be measured. Suppose you take a block of steel down below the sea level, put it under some very high hydrostatic pressure, and then you will see you will measure the change in volume, and you can find this bulk modulus. So this 3 lambda plus 2 mu is sometimes, it's easy to calculate this, easy to measure this bulk modulus, and 3 lambda plus 2 mu turns out to be 3 times the bulk modulus. Similarly, you can measure other things much more easily than lambda and mu. And these things are have different names. For example, E is called the Young's modulus. We'll see how it's measured. Uh, Nu is called the Poisson's ratio. K is the bulk modulus. This is the bulk modulus. This is the bulk modulus. And they are all interchangeable. This table gives you the interchangeability relations. For example, lambda, if you somehow have been able to measure, mu is called the shear modulus. Mu is called the shear modulus. So, for example, if you have been able to measure the Young's modulus and the Poisson's ratio, and you want to know what is lambda in terms of them, then this is what you will use. You want to know what is mu in terms of them, this is what you will use. So, depending on what constants you have been able to measure, you can find out any other constant using this table that I have given here. Okay. Now, so you need two constants. You need to measure two relevant constants, and you can get the get any other constant in terms of them. Okay. So sometimes we use this in direct notation. So remember that we have derived the strain stress relation as epsilon ij equal to Sij KL sigma KL, where Sij for the linear isotropic material, we have derived it like this. This is what we derived for Sij KL. Now, if you boil this down to the direct notation, where we use for epsilon 1, 1, we use epsilon xx, epsilon yy, epsilon zz, 1, 2, we use epsilon xy, yz, and zx, then this is a set of equation that you may have seen in your ESO 204. This is what the Hooke's law was expressed as. This is actually a strain stress relation. This is derived from the compliance Sij KL for an isotropic material, and I urge you to figure this out. Again, you will see that we are using the Young's modulus and the Poisson's ratio as the basic variable constants here, basic constants here, and whereas in the SIJKL relation we have lambda and mu. So you will have to use this table to get lambda and mu in terms of Young's modulus and Poisson's ratio. You have to change the constants, and once you do that, you can express SIJKL in terms of Poisson's ratio and Young's modulus, and from that you will be able to derive these relations. So please derive these. Please derive these equations. You have seen them earlier, and they have a very nice structure. The first thing that you note is that the shear strains, this, and this, do not depend on the normal stresses. They just depend on the corresponding shear stress. This is an outcome of isotropy. So shear strains depend only on the shear stresses. The normal strains depend on the normal stresses. But every normal strain depends on all components of the normal stresses, all three components of the normal stresses. So these are consequences of isotropy that will come in very handy while solving problems. A small addition to this, though we are not going to use this in this course very much, is that these equations that we have derived so far, the stress strain and the strain stress equations for an isotropic material, can easily be extended to a situation where the material is undergoing both mechanical deformations as well as thermal deformations. So the thing that you need to understand about thermal deformation is that thermal deformation is basically stress-free. Thermal deformation causes a stress-free strain. What I mean by that is that if you take a block of material and then you heat it by some temperature delta T, then it undergoes a strain. It expands in the three directions, but it does not generate any stress in the material. So that's why it is called stress free. But on the other hand, if you try to restrict this expansion, if you try to restrict this expansion, say you put it in a box and then you heat it, then stresses are generated. Stresses are only generated when the thermal expansions, the thermal strains are prevented, and when they are not prevented, there are no stresses generated. So the total strain in a material which is undergoing a temperature rise as well as mechanical deformations, the total strain will of course be given by the total strain here will of course be given by the mechanical strain and the thermal strain, but this thermal strain will not lead to any stresses. Stresses will only be caused by the mechanical strains. And if we assume that this is a isotropic material, so the coefficient of thermal expansion is same in the three directions, is exactly the same in the three directions, and heating causes just a volumetric expansion, then we can write epsilon ijt, the thermal part of the strain, as the thermal expansion coefficient times delta T, that's the expansion in the material in each direction, times delta Ij. So a block of material when heated does not become a parallelogram. The block expands as a block and expands by equal amounts in the two directions when a temperature rise delta T is applied. So the total strain is epsilon ij, and that is composed of the mechanical strain and the thermal strain, which is given by this. So your constitutive equation now becomes this, because this part where I have replaced, this is the part where I have replaced lambda and mu by E and nu again. You can do that yourself and see that this equation is correct. Plus, so this part is caused by these strains, and this part is caused by the thermal strains, which are simply alpha delta T delta Ij. So this is the constitutive equation. This is the compliance relation for a material which is undergoing thermal as well as mechanical straining, and this is easily derived as a consequence of what we have been discussing so far. So let's stop here.